Okay, in the meantime, I've got some trivial questions. So regarding this effective chirality, can you explain what is the difference between chirality and bi-anisotropy?
Yeah, so so in general, bi-anisotropy, so okay, I have not written this down here, but the chirality in principle is linked to the diagonal entries of the electromagnetic coupling terms. So that would be what actually chirality is going to be. Whereas bi-anisotropy is, let's say, the you would admit also all other terms to be non-zero.
Okay, excellent. So we have Michael Lapin who wants to ask a question. Please, Michael, come forward.
Yes, thank you. I probably was not the first, but I probably have a quick question anyway. So thanks a lot, Carsten. That's lots of information. And yeah, I'm just wondering, probably I missed something, but on page 24, when you mentioned that analytical condition for the resonance, unless I'm missing something, is it not so that it would only be applicable for a lossless system? Because otherwise you have mentioned indeed the divergence, which otherwise occurs.
This is I should have mentioned, this is here a lossless system. Yeah.
All right.
So this I should have mentioned this. So this is exactly so the requirement that you impose on coefficient in order to be lossless. Yeah. So
right.
As soon as there would be some losses, of course, this resonance would not appear so nicely as we have been sketching this here.
Yeah. But that's not the limitation of the whole approach.
No, exactly.
Just for this specific case.
So probably, of course, this. So I mean, so the resonance itself will appear only in the sort of clear manner here if you have a lossless material. Yeah. So if you would have some finite losses, then you would minimize your this term in order to drive this into a resonance. And I think then it's a question of what's the bandwidth of this resonance at the end. So this is then a kind of engineering question. Yeah. But this whole formalism, of course, this works exactly the same way then also for particles. I may add is that okay, I have not. I mean, I have some backup slides, but so also lossy Mie coefficients or coefficients from lossy spheres. So they can be parameterized also with two angles. And indeed, both of these angles, they go from -π/2 to +π/2. And then you would simply have two angles to parameterize the Mie resonance of a lossy sphere. That would amplify a bit the parameter space in which you have to search for. But the principal applicability continues to be exactly the same.
Yeah. All right. Yeah. Thank you.
So we have another question from Stravula Fotanopoulos. Please, Stravula.
Hello?
Come forward.
Can you hear me?
Can't hear you.
Can you hear me?
Yeah,
now better. Yeah.
Okay. Thank you, Carsten. That's a great talk. You said that in your T-matrix method, it's a method based on discrete objects. I had two questions. In the case of, let's say, ordered metasurface, are there any filling ratios that above which the method, I mean, what is the range of validity? How high the filling ratio of the structure can be for the method to apply?
Yeah.
In the case of disordered metasurfaces or photonic crystals, for that matter, again, how dilute does the sample need to be, in the sense, if you have like some probability to have dimers in your structure when you're introducing disorder, how does that affect the method? If you could.
Okay. Maybe so concerning limitation on the aspect ratio, maybe this is something. So maybe I should have made a page basically for this, but I don't have. So what is like first assumption is that approach is correct to describe fields in the far field and near field, if the circumscribing sphere of the objects do not intersect. So if you have like, I hope I'm visible here. So if you have two cylinders that are parallel to each other and extremely long, so then the method would have problems to describe the field in the circumscribing spheres of each of the cylinders. But the field outside that circumscribing sphere, that is still, so nevertheless, that puts you some limitations on, like you cannot discuss the interaction of a quantum emitter then with these kind of systems. Yeah. So this is a kind of limitation. So this is not a limitation per se. So we and all the other people are working on a concept that is called a distributed T matrix. So, and in this distributed T matrix, so this is pretty much the same as the T matrix as we have it, but it's just that you do not consider like a single coordinate center as the point of the expansion, but you distribute your T matrix representation actually across the object. And this allows then also to describe arbitrarily free objects just with such a distributed T matrix. And this is then also the key so to discuss objects with an arbitrary aspect ratio, and you can put them arbitrary dense. If you, of course, then calculating this distributed T matrices is a bit more elaborated and more complicated, but in principle, this is feasible. And then you can convert this directly into the same formalism as we have it here. So this is currently under development. So this is not yet published, and I also have no slides on this here. But this is not a intrinsic limitation of the problem, but this can be circumvented. And as such, in principle, there is no. Or what was then the second part of the question? So whether I mean, so then I can handle arbitrary filling fraction. This can be arbitrarily diluted. Yeah, so this can be very nicely handled, and because basically this doesn't matter really at this point. Yeah, and it can be also arbitrarily dense. Yeah,
thank you very much, Carsten. Thank you.
Yeah, thanks, Dr.
Excellent, Carsten. I have a second question, which is another trivial question. So when you look at your helix, did you look at the case of weak twist?
So weak. What do you mean by weak twist?
It's really elongated. So the periodicity is very large because you can have some asymptotic procedure.
Yeah. So
so here, obviously, what you show is very small, the pitch, the periodicity, so it means that it's densely packed.
Yeah.
The other extreme case.
Yeah. This I don't know. So in this sort of Bayesian optimization, we put like an upper and the lower bound on all geometrical parameters that mattered here to us. And that's why we haven't looked into this case. So the algorithm had not been stopping one of the bounds actually that we have been imposing. So neither an upper nor a lower bound. So if you would have stuck to a lower bound in, for example, this pitch, so pitch it's called, so then we would have changed probably something. But this was not the case, and at least for our purposes, this was not necessary to consider this. But in general, I do not think that there is a major limitation also to look into much more extended structures. Yeah. If this gets like very extended structures, the only bottleneck that you have is that you might be required to take very higher order multiple moments in order to describe the response. But I would not see a fundamental problem that would prevent you from considering also very elongated helices.
And I have a question. I mean, again, not an expert on chirality, but I did a bit of bi-anisotropic media using some homogenization procedure. And can't you also reinterpret your work in terms of a bi-anisotropic medium?
Yeah. So indeed, this is so I mean, what you can do, and this is also what I mean. This is a part of this last work, but we are also making dedicated articles to this. So what is really possible? So once you know this renormalized T matrix,
yes.
So there is really a one-way calculation to effective material parameters.
Yeah.
So, and this works actually for both local material parameters, so up to the bianisotropic level, but this also applies actually to non-material parameters. So we also have been looking into considerable relations with where the dependency of the response depends on higher order gradient fields. And even these non-local considerable relations can be described with this formalism. So this is up to the local level. This is already contained in here, because as I said, so I mean this molecule itself, this was archival, yeah. So that's why chirality did not emerge. But if it would have been a chiral molecule, then there would be a bianisotropy really emerging here, and we can really directly calculate the effective probability. So this was here a matrix, yeah, and because this was an isotropic material, but the anisotropy was very weak. So the anisotropy, for example, is responsible here for the splitting of these resonances, and also we see here, so the splitting of these resonances. So, and this is an effect due to anisotropy. If you switch off this anisotropy, this is going to vanish. Yeah, so, but we can also make then here a modal analysis considering an isotropic material.
Excellent. So we have again a question, and this is great news. And again, a question from Michael. Please, Michael.
Yes. So another thing, again, probably I'm missing something, but when I think back on the structure of these T matrices, which you have described in the very beginning, eventually each of the submatrices is a collection of effectively expansion in multiple terms. So is it right that you eventually truncate each of them at some stage, depending on the degree how far you'd like to go, right?
Yeah, exactly.
And then my question is, because that's still a complete matrix with several submatrices, is it not a problem that, but still you want to make it symmetric? I mean, not symmetric, but equal in terms of these subparts. Is it not a problem that you may effectively discard some of the smaller terms to a different extent? Like let's say this matrix still is a sparse matrix, but you might be missing some of the terms which are greater, more different from zero than some other zeros you actually include. Does that actually make a problem?
No, I think this is of course fully correct. I mean, so the way as it's described here, maybe it might make sense to start here at this slide. So of course, this expansion here is only exact if you sum up to infinity. But of course, this is neither practical nor computational possible, but also technically not necessary, because the objects, if they are discrete and localized somewhere in space, so they will interact extremely poorly with light of a pretty large angular momentum, and that's why these T matrices, Michael, here you are absolutely correct. So they are always non-zero. Yeah. So in these higher order terms, as long as they are not symmetry forbidden, so they are always non-zero. But for practical purposes, we have to cut this down. And then indeed, this is a question of up to which point you need to cut this down. But here we are simply trained to do this analysis with an increasing number of multiple moments, and then to study the convergence of any observable property that you are interested in. And if you say that you would like to know the CD signal up to 1% accuracy, then you know that you might have to go to the octopole, or you might have to go to n equal to 4. Sometimes we do this also with n equal to 8. Yeah, so I don't even know how then these multipoles are called, but this is possible. These matrices get large, but this is not a fundamental thing. Yeah, and so this is not so easy to say a priori of how many multipoles you should retain in your expansion. And so you get a bit of an experience in the course of time of what is necessary. Yeah, so in the case of doubts, you always have to check this. Yeah, but this is something that you would have to do with any other numerical technique as well.
Yep.
Yeah, so this is always an approximate solution to Maxwell's equations, and you have to study that you have been sufficiently converging to get accurate results. And this is just one of the parameters that one has to check for.
Yep. Yeah. All right. Yeah, that's more clear. Yep. Thank you.
Okay, do we have any more questions in the audience? It's a unique opportunity to interact with Professor Rockstuhl, who is an expert in this area. Okay, I have some questions here again. This is a very trivial question. It's about, you know, these deep learning techniques that you're using. Could you tell us just a little bit more about this? Because, well,
yeah, okay, so yeah, I mean, so there are, or do you have a more specific question, or do you just would like to know what type of applications do you have in mind at the moment, or?
So how do you do your training on your side? How do you proceed?
So maybe this sort of Bayesian optimization, this is not a deep learning technique. But this is still a, this is, I mean, people don't like this, but this is still supposed to a global optimizer. So in this Bayesian approach, you basically assume a kind of stochastic or Gaussian process. So that allows you
Bayesian.
It's by Bayesian, yeah. So that allows you to get a kind of educated guess of what is the most promising next point in parameter space that you should evaluate in order to optimize the objective function in a kind of global sense. So,
but here, so your object is an helix. So you have so your parameters are what? So this is the diameter of this tube.
Okay, so the radius of the helix, the thickness of the wire, the pitch, the number of turns. And this is a kind of rounding effect, if I remember correctly. So the helix is like rounded at the end.
Yes. And so this is the number of turns in each unit cell, you mean?
No, this is an isolated object. So that's why there's anyhow, this is just one object.
I see.
And I can calculate the T matrix from this object, and then I can pin this number, so this normalized electromagnetic chirality to it.
Yeah.
And then my algorithm is going to maximize this. Yeah.
Okay. And
I mean, so the work with neural networks. I mean, still there is this sort of far-reaching goal that you would like to solve actually the inverse problem. For in the scattering setting, and that means that you would like to I mean, so you would like to know a T matrix, and then you would like to know a scatterer that is able to provide you exactly that T matrix. And this is a kind of inverse problem, and in the best possible world, so you even constrain the search to that parameter space that is also experimentally accessible. So it doesn't make much sense to design an object that cannot be fabricated, but it's helpful to restrict the search to the parameter space that is also experimentally accessible. And this is certainly this is a kind of far-reaching goal, yeah. The crucial point here is let's say availability really of T matrices on which we can train these artificial neural networks. So. I mean, we in our group we have been standardized also the way we represent these T matrices so that we can compare, we can accumulate data, and I would be happy actually in the long run so to make kind of white paper also where we invite the community to discuss at least possible standards of how to store T matrices so that you could exchange actually all T matrices that have been ever calculated on the world among each other. So you build up like a global database of T matrices here. That sounds like a pretty promising way, yeah, so to generate at least a lot of data on which you can train neural networks.
Yeah, you would have enough data to train it well.
This,
is asking a question. Please, Maxime, come forward with your question. You are mute, Maxime. You have to unmute yourself.
All right. So, Carsten, thank you very much. Can you hear me now?
Yeah.
Yeah. So just an advice. I mean, this is what we are doing, but I think there will be a lot of space for everyone there. If you try to optimize the scatterer, like you do on this slide, maybe it's a good idea to look at the eigenmodes, eigenstates, or those quasi-normal modes, so to say, because if you have a scatterer and it supports only one resonance, for instance, then you can already evaluate, I think, the scattering from all directions, because there are certain integrals where you can express it with I mean, if you can possibly formulate what shape your current this has to be in order to achieve something that you need, then, I mean, talking about this reverse engineering, then you probably can think of a particle which would support such an eigenstate with such current distribution. We're trying to do this for metasurfaces, like from only one direction. So, but I mean, if you are interested in those in any other directions, it's doable also. Just try to maybe try to think in this direction.
This is certainly helpful. I mean, I'm pretty much aware that there are many different approaches, and this is not a kind of unique mindset that we have here. So there are other people working along similar lines. The question with the quasi-normal modes, or whether we are going to use a T-matrix representation, this is a bit more of a fundamental type of aspect of how we want to discuss the scattering process. So I think this has both had pros and cons, I think. I think both are valid approaches, but we have specialized here on these T-matrix things.
And by the way, we also call it S matrix, but I don't mind. Scattering matrix. It's coming from quantum mechanics. Actually, people used to write the letter S, but anyway. So thank you.
Thanks, Maxime.
Great. We have actually Jua who left a nice message. Thank you for the very interesting talk. Unfortunately, I have to go now. And then Tabakov Pakizev, interesting works. Thank you for sharing and your time. So I really have the same feeling that it's really, really interesting. So do we have any more comments regarding all these exciting effects of chirality? By the way, the upper bound, normalized upper bound, Carsten, you confirm it was 1. You cannot go above 1.
You cannot. With passive objects, of course.
Okay, but I think also, I think in terms of your governing equation, you might even lose existence and uniqueness of the solution if the chirality is too large. No, you might have such issue. No, you can't have too much of chirality.
So
defined by the Maxwell-Telegan equations, and I think, Abiba Mari has shown some results in this direction, perhaps. Okay. I find, yes, so Michael says, many thanks, Carsten, and great to see everyone. Yeah, likewise, it's very good to see all you all guys. Okay, so do we have any more comments? Otherwise, we will thank our fantastic speaker again.
I mean, thanks also you for the discussion, for for your attention, for the interest also in the work, and can just hope that we see each other on a conference again somewhere soon in real.
Yeah, perhaps in Siena actually. Perhaps.
Exactly. So I will be there.
So 2022. Yeah. Okay. Thank you so much, guys, and wonderful talk, Carsten. It's really magnificent, and people, you can watch it again. Then it will appear on the webpage of MetaMAT, and you can also watch the previous talks there. It's permanent. Okay, bye-bye, guys. Stay safe.
Bye-bye, everybody.